For over a decade, the industry has repeated a specific mantra: NoSQL for scale and speed, SQL for structure and safety. We were told that by removing the overhead of joins and rigid schemas, we would unlock massive performance gains. But as our systems matured, we realized that performance isn't a single number on a benchmark. It's a function of your data access patterns. Today, we're deconstructing the NoSQL lie. We'll look at the hidden costs of application site joins, the reality of network latency, and why modern SQL engines are often significantly faster for complex relational data than their document-based counterparts. It's time to stop choosing databases based on hype and start choosing them based on computer science fundamentals.
The most common argument for NoSQL is that joins are slow. While it's true that joining massive tables requires compute, NoSQL doesn't actually eliminate the need for relationships. It just moves the join logic from the database to your application code. Imagine fetching a user and their last 10 orders. In SQL, this is a single optimized query. The database engine uses its query planner to find the most efficient path. In a typical NoSQL setup, you perform one query for the user, then a second query for the orders based on the user ID. This is the N+1 problem in disguise. You are trading a highly optimized C++ or Rust join inside the database for multiple network round trips and manual data stitching in your application. In high concurrency environments, those extra network hops are almost always slower than a local join.
Let's quantify that network cost. Internal database operations are measured in microseconds. A network round trip between your app server and database, even in the same availability zone, usually takes between 1 and 5 milliseconds. If your NoSQL pattern requires 4 sequential lookups to render a single page, you've just added 20 milliseconds of baseline latency before the database has even done any work. Meanwhile, a complex SQL join might take 3 milliseconds of CPU time, but only 1 millisecond of network time because it returns the entire result set in one go. As your data complexity grows, the flat structure of NoSQL forces more round trips. In the world of distributed systems, I/O is almost always the bottleneck, not CPU. By reducing the number of round trips, SQL's relational model often delivers a faster time to first byte for the end user.
Modern SQL databases like PostgreSQL have spent 30 years optimizing their query planners. When you write a SQL query, the engine doesn't just execute it. It analyzes the statistics of your data, looks at available indexes, and decides whether to use a sequential scan, an index scan, or a bitmap heap scan. Many NoSQL databases offer simpler indexing strategies. While they are incredibly fast at primary key lookups, their performance can degrade rapidly when you filter by multiple non-indexed fields or attempt complex aggregations. SQL engines can use techniques like index-only scans, where they don't even touch the actual table data if the index contains everything needed. This level of sophisticated optimization is why SQL can often handle analytical queries on live production data far more efficiently than a document store that might require full document parsing for every filter.
What about writes? The NoSQL speed advantage often comes from deferring durability. By using log-structured merge trees or eventual consistency models, some NoSQL databases can accept writes in memory and acknowledge them before they hit the disk. This is undeniably fast, but it's not magic, it's a trade-off. SQL databases typically prioritize ACID compliance, ensuring that once a transaction is committed, it's safe even during a power failure. However, modern SQL engines have bridged this gap. Features like asynchronous commit in Postgres allow you to choose NoSQL-like write speeds for non-critical data while maintaining strict safety for financial records. When you normalize the durability guarantees, making sure both databases are actually saving data to disk, the performance gap often vanishes. The speed of NoSQL wasn't always better architecture. Sometimes it was just less work.
One of the final nails in the NoSQL is always faster coffin was the introduction of optimized binary JSON types, like JSONB in PostgreSQL. This allows you to store unstructured document data inside a relational table, index specific keys within that JSON, and even join that JSON data against traditional relational columns. You get the flexibility of a document store with the power of a relational engine.
Benchmarks consistently show that PostgreSQL's JSONB performance is competitive with and sometimes faster than dedicated document stores like MongoDB for common retrieval patterns. You no longer have to choose between a rigid schema and a fast document store. You can have a strict schema for your core entities like users and accounts, and a flexible JSONB column for dynamic metadata, all within a single high-performance engine.
So is NoSQL a lie? Not entirely. For massive scale write-heavy workloads with simple access patterns like sensor logs or social media feeds, NoSQL's horizontal scaling is still king. But for the 95% of applications that deal with complex, interrelated data, SQL is not just safer, it's often faster. The NoSQL is faster myth was born in an era when SQL engines were less optimized and hardware was more constrained. Today, with NVMe drives, massive RAM, and sophisticated query planners, the overhead of the relational model is negligible compared to the architectural mess of manual data stitching. Next time you start a project, don't reach for NoSQL because you think it's faster. Reach for it only if your data is truly non-relational. Otherwise, trust the decades of engineering in your SQL database. Your latency and your developers will thank you.